Hello, AP Chemers. Let's draw some covalently bonded molecules and look at the electron geometry, molecular geometry, bond angles, hybrid, and the polarity of these molecules. So let's start with NH3. Nitrogen has 5 valence electrons. And we are going to bond it to 3 hydrogens. So one goes here, one goes there, and then one goes here. The electron geometry has to do with how many areas of electrons there are. So there are 4. So the shape that the electrons are making is a tetrahedral. Now, just so you know, on the AP exam, I've never seen them ask for the electron geometry. They always ask for the molecular geometry. If they ask you for the shape or the geometry, they're talking about the molecule itself, the molecular geometry, unless they specifically say electrons. So the reason why we care about the electron geometry is if you know the electron geometry, that kind of helps you figure out the molecular. It also helps you figure out the bond angles and all that. So because it's tetrahedral, we know that the bond angles are 109.5. We also know the hybrid is going to be sp3 since there are 4 areas of electrons, 1 s and 3 p's need to mix. And for the molecular geometry, we know that we have a nitrogen and then we have 3 things that are 109.5 from each other. So that kind of looks, I guess I could have drawn it the other way. Let me draw it this way. And so that looks like a pyramid. And so it is trigonal pyramidal. For the polarity, we know that it is polar and the direction of the dipole goes this way. Nitrogen is more electronegative than the hydrogen, so you have, I guess I could have drawn the little, let me draw them for you. So you have this little one, this little one, this little one for a net of going towards the nitrogen there. Okay, let's look at H2O. So oxygen has 6 valence electrons. And we need to bond it to 2 hydrogens. Here's 1 and here's 1. There are 4 areas of electrons, so that automatically makes it a tetrahedral for the electron geometry. The bond angles are 109.5. The hybrid is sp3. And then for the geometry, we have the oxygen. We have 2 things coming out at 109.5, so that's a bent or an angular. And that is definitely polar. So if you draw the little arrows, there's 1, there's 1. So the net would be towards the oxygen. So it is polar. So if you are going to draw your little arrows, that is totally fine. Just draw them really light or something because they will want you to show the net direction of the dipole moment. And so they want you to show this net arrow. They don't want to see those. So you can draw them to help yourself figure out what the net arrow looks like, but make them really light or erase them. Make sure that it's obvious that it's this one. Just a little note here. So we know that because you have lone pairs, the angle is not exactly 109.5, it's more like 104.5. That's something you would need in college to know, but for the AP exam, they're totally fine with the 109.5. So just stick with 109.5. Okay, Nh4 plus. So for Nh4 plus, nitrogen normally has 5 valence electrons, but the plus means you lost 1, so I'm going to only draw nitrogen with 4. And there are 4 hydrogens that I need to bond to it, so there's 1, 2, 3, and 4. And because it's an ion, I gotta use brackets and put a positive there. Around your central atom, there are 4 areas of electrons, so the electron geometry, the shape that the electrons make is a tetrahedral. the bond angles are 109.5, and the hybrid is sp3. Again, all that is because there are 4 areas of electrons. For this shape, you have your nitrogen, and then you have 4 things at 109.5, so that is also a tetrahedral. And whenever you don't have any lone pairs on the central atom, the electron and the molecular geometry are always going to be the same. For the polarity, we know that nitrogen is more electronegative than the hydrogen, so they all are pointing towards the nitrogen, but they all cancel out because they're all evenly spaced, and so it is nonpolar. Okay, let's look at the next one. Got CCl3F. So we have a carbon and 3 chlorines and 1 fluorine. Now remember that carbon can have up to 4 bonds. Halogens, whether it's chlorine or fluorine, can only have 1 bond typically. And so this tells me that the carbon is in the middle. Carbon has 4 electrons, so it's going to bond to a fluorine and 3 chlorines. Each of those have 7, so we're going to use 1 for the bond, and then we'd have 3 lone pairs on each of those. Make sure that you are drawing your lone pairs. I know it's kind of annoying, but if you don't draw your lone pairs, then it will be marked incorrect, whether on the AP exam or on my test. So you look, there are 4 areas of electrons, so the electron geometry is tetrahedral. The bond angles are 109.5, and the hybrid is sp3, again, all because there are 4 areas of electrons. For this shape, there are no lone pairs on the central atom, which tells me that the electron and molecular geometry are the same, or you can think, oh, I have a carbon, and 4 things coming out at 109.5, so it looks like a tetrahedral. Now, if all of these were chlorines, then it would be nonpolar. Fluorine is more electronegative than carbon. Chlorines are also more electronegative than carbon. And so those electrons are being pulled in all equal directions, correct? So you would think they cancel each other out. And if this was a chlorine, they would all cancel each other out. The problem is, this is not chlorine, this is fluorine. Fluorine is more electronegative than chlorine is. So even though these electrons are all being pulled towards those chlorines, and these electrons are being pulled towards fluorine, fluorine is stronger in pulling those electrons. So the net is going to be towards that fluorine. So that one is polar. It's a tricky one. Remember that one of the ways to figure out if it's polar or not, and it works like 95% of the time, is if you look at the center of your molecule and look around to see if everything is the same. And obviously those are not the same thing. Same thing with the water here. Oops. So with the water, when we drew it this way, it was obvious that there is a net dipole. But if you drew it this way, you know, you might think, oh, there's polarity here, and these are being pulled in. You might think that they cancel, but they don't, because in reality, it's a bent molecule. And so one of the tips is to not just rely on one method, but to always look at both methods. And so if you look at your center, lone pairs are different from hydrogens, and so that confirms that it is polar. Okay, HCN is next. So hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. So I'm going to draw it first kind of messy, and then I'll redraw it. Carbon, we said, has 4. Here we go. So we bond those 2. We bond those 2. Now hydrogen's good with its duet, but carbon right now has only 6, and nitrogen also only has 6. So let's double bond them. Now carbon has 7, nitrogen has 7. So let's triple bond them, and now everybody's good. So I'm going to rewrite this. Ignore this here. So it should look like this. Always redraw so it looks neater. If you look at your carbon here, there are 2 areas of electrons, And so the electron geometry is linear. You don't have any lone pairs on your central atom, which tells you that its molecular geometry is also linear. Or you can think, oh, I have a carbon, two things bonded to it at 180 degrees, since it's a linear electron geometry. The hybrid is sp because you have two areas of electrons, so one s, one p need to mix together. And then the polarity here, carbon and hydrogen are actually pretty similar in electronegativity. Maybe the carbon is slightly more electronegative, but the nitrogen is definitely more electronegative than the carbon. And so the net will be going towards the nitrogen. Again, I would not leave it that way on the test. I would erase those little arrows or something. You just want the big one, or make them super light so that it's not confusing where your net dipole moment is. This one is polar. All right, SO4 2-. So you can try to draw SO4 2- in different ways. You can draw your S and your 4 oxygens, each with 6 valence electrons, and then say that -2 means I add 2 more electrons and put them in the spot that would fit them. Or you can do the math. The problem with the math, it only works if you have your molecule obeying the octet rule. But let me review the math real quick with you so that you remember how to do it. So for the math, first you count how many valence electrons are actually available to you. Actually, how many valence electrons would everybody need to be stable? So we have a sulfur, it would like an octet. We have 4 oxygens, they each would need an octet. So to make everybody stable, you'd need a total of 40 electrons. Okay, then you count how many valence electrons are actually available to you. So sulfur has 6 valence electrons. Each of the oxygens also have 6 valence electrons. But then that -2 means that you also have 2 more available to you. And so altogether, that's 32 electrons that are available. Now I need 40 electrons to make everybody stable. I only have 32. The difference between them is those electrons is how many electrons are bonded. Now each bond takes 2 electrons, so what you do is you divide this number by 2, and this gives you the number of bonds. So then what you do is you draw your skeleton, so sulfur and then 4 oxygens. You connect everything once with single bonds, and you count how many bonds you've drawn. I've drawn 4, and look at your math. You were supposed to draw 4, so that's good. You're done with the bonds. So then what you do is you give everybody an octet with lone pairs. So this sulfur is good already. It has the 8 valence electrons, but each of these oxygens need 3 pairs. Ooh. There we go. Then, really important, you need to count that you've drawn the correct number of valence electrons that are available, which means check that that number is correct. So I'm going to count in pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs, which means 32 electrons, so that is good. Now let me no, can't get it in between. Oh well. Let me try to show you how I would have done this SO4 2- without doing the math. It's a little bit more work, but you can kind of try it if you want. So sulfur normally has 6 valence electrons. 1, 2, 3, 4, 5, 6. Then we have 4 oxygens. Each oxygen has 6, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. All right. We also have 2 electrons available to us, 2 extra electrons. So put them anywhere you want, and you can move them after. So I'm going to put one maybe here, so that these are a pair here, and maybe I'll put another one there. Okay, so I drew all my available electrons. Now I try to connect everything. So I'm going to connect these 2 here, maybe these 2, and then these 2, and check that everybody has an octet and see if there's something you could do to change things. So based on the way that it is right now, this one is pretty good. This oxygen is pretty good. It has 1, 2, and then 3, 4, 5, 6, 7, 8. So that one's good. This one right here has too many. Wait, no, that's good. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen is good. So this oxygen is good. This oxygen is good. Let's look at this oxygen here. 1, 2, 3, 4, 5, 6, 7. This one needs 1. Then this one, 1, 2, 3, 4, 5, 6, 7. This one also needs 1. Now let's look at the sulfur. We have 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. Sulfur has too many, has 2 extra. And each of these oxygens need 1. So I'm going to take this one right here, and I'm going to just cross it out here and put it there. I'm going to take this one, cross it out, and put it there. And look, everybody now has an octet. So then I just rewrite it so it looks neater. Each of these have 3 lone pairs. And then because it has a charge, I put a 2-. So, you know, either way is fine. Some people prefer the math, some people prefer this. This will always work no matter what, but the math will only work if it's obeying the octet rule, and it's probably a little bit easier to do than trying to figure out where to move your electrons, but it's totally up to you. Okay, we never really answered the questions here, so we put brackets around in a 2-. And the electron geometry, I have 4 areas of electrons, so tetrahedral. No lone pairs, so also tetrahedral. 4 areas of electrons means 109.5 degrees. Hybrid, 4 areas of electrons means sp3. And then, is this polar or not? Let's see. So oxygen's more electronegative than sulfur. So you draw these 4 arrows towards each of the oxygens. Looks like they all cancel out. So again, I would erase all of these because there is no net dipole moment and it is nonpolar. Okay, let's look at resonance structures. So we want to draw SO3. So again, you can draw your 6 valence electrons for each of the sulfurs and each of the oxygens and try to move them around, or you can do the math. I'm going to go ahead and do the math just so we can practice a little bit more. So originally I want to figure out how many valence electrons needed to give everybody an octet. So we have a sulfur, it needs 8. We have 3 oxygens, each need 8 for a total of 32. Then we have what's available. Sulfur has 6. Each of the oxygens also have 6 for 24 electrons available. I subtract the 2 to get 8 electrons that are bonding. divide by 2, and that gives me 4 bonds. So then I draw my sulfur. I have 3 oxygens around me, so I'll do 1, 2, 3, connect everything once. And I drew 3 bonds right now when I connect everything, but my math tells me there are 4 bonds. So well, there's 3 different options where I could put it. I could put it here, or I could put it here, or I could put it down here. These are all options. That's because these are all resonance structures. They're all valid resonance structures. Between resonance structures, you draw a double arrow. And we're not done yet because we don't have our lone pairs, right? So let's check our lone pairs. The sulfurs each have 4 bonds, so they have 8 electrons, so they are all good. The oxygens that have a double bond, that means 4 electrons, so they need 2 lone pairs. So same thing with that one, and same thing with that one. The oxygens that are only single bonded, that means they have 2 electrons, so they need 3 lone pairs. So same thing for all of them. And to make sure, you got to check that you've drawn the available electrons. So we need 24 electrons, which means 12 pairs. So I'm going to count in pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you should count all 3 of them just to make sure they check. So these are the resonance structures. The electron geometry here is trigonal planar because we only have 3 areas of electrons. The molecular geometry is the same. The bond angles, call it BA for bond angles, 120 degrees. The hybrid is sp2, 3 areas of electrons, 1 s and 2 p's need to mix together. And then for polarity, all of these are equivalent. So it's in reality, remember with resonance structures, it's not that these are 2 single bonds and this is a double bond. In reality, there's a bond and a half to each of those. And so they are going to pull with the same amount of force, and so, or attraction, I should say. And so this is non-polar. Okay, let's try CO3 minus. So we're going to, you can do the math, or you can, if you'd like, just move around your electrons. I'll do the math. So carbon needs 4, each of the oxygens need, carbon needs 8, each of the oxygens need 8. So for a total of 32 electrons needed. What's available, carbon has 4. Each of the oxygens have 6, but then that -2 means we have 2 extra electrons available to us. So what is that? 24. Subtract the 2, you get 8 electrons that are bonded, and so that's 4 bonds. Divide by 2. So then you draw your carbon. You have 3 oxygens. So put 1, 2, 3. Connect everything once, and then you've drawn 3 bonds, but the math says 4 bonds. So now, just like this one, you have 3 options. So I'm going to draw 3 of these. So I can put the double bond here, can put it, oops, it's the same spot. There we go, kind of. Anyway, so I can put it there instead, or I can put it here. And then give everybody an octet. The carbons all have 4, so they're good. The oxygens that are double bonded, they need 2 lone pairs each. And then the oxygens that are single bonded, they need 3 lone pairs each. So very, very similar to our SO3 here that we just did. One difference is because this is an ion, we got to put brackets around in the charge. We didn't need to do that with SO3 because it was not an ion. And then you need to draw double arrows between each of the resonance structures. And of course, check that you've drawn 24 available electrons, which we have.